All right, today we're going to tear into a really fascinating paper from Metafair. It tackles a problem that, let's be honest, every single one of us who works with LLMs has run into. You generate a bunch of different answers, but how do you know which one's the right one? The paper's title kind of gives the game away. The majority is not always right. Let's get into it. You've definitely been here. You give a model a tricky reasoning problem, you tell it to generate, say, 10 different potential solutions to boost your odds, and you get back a whole smorgasbord of different answers. So the million-dollar question becomes, which one do you actually trust? And that, right there, is the heart of the problem we're digging into today. So here's how we're going to break it all down. First, we'll set the stage with the LLM reasoning problem. Then, we'll look at why the go-to method, majority voting, just doesn't cut it. And then, the main event, a deep dive into the paper's solution, AggLM. We'll cover how it's trained, how it performs, and what this all means for the future. So, you know the drill. If you want to get those state-of-the-art results on really tough reasoning tasks, one of the best strategies is to just throw more compute at it during inference. That usually means generating a whole bunch of independent solutions for the same problem and then just picking the best one. It's a really powerful technique, but it creates its own bottleneck. And that's the absolute crux of the issue. We've gotten really good at generating dozens of potential answers. The bottleneck is actually shifted away from generation and moved squarely into aggregation. How in the world do you sift through all these different ideas to find or maybe even build the right answer? All right, so let's talk about the old school method that pretty much everyone uses, majority vote. You might also know it as self-consistency. It's been the standard for years, but as the paper's title hints, it's got some pretty serious flaws. The logic behind it is beautifully simple, right? If the model spits out the same answer most of the time, that one's probably the right one. It feels right, and honestly, for a lot of things, it works just fine. But what happens when the problem's really hard, and the correct answer is super nuanced? Well, in those cases, the model might make the same mistake over and over again. And suddenly, majority vote is just amplifying the most popular wrong answer, completely ignoring a brilliant correct solution that's hiding out in the minority. The authors themselves put it perfectly here. When you just count the votes, you're basically agreeing to throw away the needle in the haystack. So this begs the question, instead of relying on this simple rule, what if we could actually teach a model how to find that needle? And that is where this paper's big idea, AggLM, comes into play. The fundamental shift here is to stop thinking of aggregation as some fixed, dumb rule. Instead, what if we could treat aggregation as an actual reasoning skill, something a model can learn and get really good at? And this, right here, is the real conceptual jump. The goal isn't just to look at a list of answers and pick the best one. No. It's to review all of the candidates, pull out the good ideas, even from the wrong answers, and then synthesize a brand new final answer that's actually better than anything in the original set. So, to get formal for a second, an aggregation language model, or AggLM, is a specialist. It's a model trained for this one complex job. You give it the problem, you give it all the candidate solutions, and then you train it using reinforcement learning to get really, really good at this process of reviewing, reconciling, and ultimately building the best possible answer. The whole process is actually pretty straightforward. First, you generate your candidate solutions, just like you always would. Then, you bundle up the original problem and all those answers into a single big prompt for the AggLM. Now, the real magic is in the training. For things like math problems, there's a definite right or wrong answer. So you can give the model a super clear reward signal. You get a 1 if you're right, a 0 if you're wrong. This lets them use RL to fine-tune the model, basically teaching it which lines of reasoning are gold and which are just dead ends. So how on earth do you train a model to do that? Well, this is where we get into the real secret sauce of the AggLM method. It's not just about the data you throw at it, it's about the kind of data. What the authors figured out is that the secret is feeding the model a very specific, carefully balanced diet of problems. See, to build a really robust aggregator, the model needs to learn two totally different things: when to trust the crowd, and crucially, when to ignore the crowd and go hunting for that one correct answer. So they defined two kinds of training data. First, you have easy examples. These are problem sets where the most popular answer is in fact the right one. This teaches the model, hey, sometimes the crowd is right. But then, and this is the important part, you have the hard examples. These are sets where the majority answer is flat out wrong. These are the examples that force the model to learn the much tougher skill of spotting and trusting a correct answer that only one or two solutions came up with. And check this out. This is how they actually mixed the training data. It's so clever. They take all of the hard examples they can find, every single case where the majority is wrong, and then they mix in only about half of the easy ones. Why do that? Well, by over-indexing on these tough cases, they're preventing the model from just getting lazy and learning to vote with the majority. They're forcing it to become a detective, to develop that robust skill of finding the correct minority opinion, which is the exact thing that majority voting is terrible at.
Okay, this training strategy sounds amazing in theory, but you know what really matters? Does it actually work in the real world? Let's get to the results and see how AggLM actually performs against the competition on some really hard math benchmarks. So here we are looking at the AIME 25 datasets, and they're aggregating answers from a 1.7 billion parameter model. Majority voting gets you to about 46% accuracy. And what's really interesting is that if you just prompt the base model to aggregate without special training, performance actually gets a little worse. But then you look at the RL-trained AggGM, and bam, 50% accuracy. Now, a 4-point jump might not sound like a lot, but on a competitive Math Olympiad dataset like this, that is a huge deal. This isn't just some tiny improvement. It's clear proof that teaching aggregation as a specific skill gives you a real, measurable boost over the old way of doing things. Okay, but hold on. Here's the critical question every engineer watching this is probably thinking. The AggLM was trained on answers from a little 1.7B model. Is it just overfit to that one model's weird quirks? Or can it actually generalize that reasoning skill to handle answers from a much bigger, much stronger model? And would you look at that? The answer is a resounding yes. Check this out. It's the same little 1.7B LAGL model, but now it's looking at answers from a way more capable 8B model. And even in this totally out-of-distribution scenario, it still beats majority voting. This is incredible. It shows the skill it learned is actually robust and transferable, which is just fantastic news if you want to use this in practice. So we've established AggLM gets you higher accuracy, which is awesome. But there's one more major benefit that makes this whole approach incredibly compelling, and it all comes down to efficiency. Let's talk about cost, tokens. Generating a full chain of thought answer for these hard problems is super token intensive. We're talking over 10,000 tokens on average. But the AggLM model isn't starting from scratch, it's just synthesizing from existing text, and that makes it way more efficient. It uses less than a third of the tokens to create its final, more accurate answer. And that right there is the killer combo. With AggLM, you're not just getting better answers, you're getting them for a fraction of the inference costs you'd pay to just generate more and more samples for a majority vote. It's a total win-win. Higher accuracy, lower cost. This just opens up so many cool possibilities. Now, look, the authors are clear. This isn't a magic wand. The aggregator's performance is still capped by how good the initial answers are. If none of the candidates have any correct reasoning, it can't just invent it out of thin air. But the core idea here is incredibly powerful. We can actually isolate a specific, complex reasoning skill and train a specialized model to master it. And that just leaves us with this thrilling question. If we've taught a model to aggregate, what's next? Verification? Critique? Planning? We might just be at the very beginning of an era of specialized modular reasoning skills.